I think I got a good high level intuition, and probably have to do some reiterations in terms of what the the Fourier transform is doing and why the integral makes sense. But I was not. I think I didn't get to the point where, and I don't really understand why is it that multiplying by a complex exponential makes sense mathematically speaking. Because I got stuck with the. I was trying to do an example with the sinus function, right? And then that turned out to be a bit more complicated than expected. Which I also didn't know exactly why, because I thought that should rather be the easy case, right? And so, how can we go about these? So we have basically, let's open up the Wikipedia, Fourier transform integral. Same thing as usual. There we go. English. And so the integral, there you go. So this is the one that we're looking at, and why does this mathematically make sense, right? So complex exponential, like there is a really nice video from 3 Blue 1 Brown, 3 Blue 1 Brown I don't know if that's the way. This is this one, so let me see if I can tune the audio. I think it's already low, so it does not blow up your ears. Because he basically
way
to
think about the function e to the t is to ask what properties does it have. Probably the most important one, and from some points of view, the defining property, is that it is its own derivative. Together with the added condition that
there is a point in time in the video where he explains, and I found this super nice because he explains why, like in the complex plane, right? Like in terms of these dynamics, why. So what is it that e to the power of x is doing, right? Which is this kind of like circle thing. Exactly. So essentially, that's what you have. And so times 2 pi, that's the full circle, right? Now, why would that make sense? And so we also have this expansion. But why would that make sense? As in, like, the integral of these is kind of, it's really interesting because the okay, here's the theory. It just now it kind of like yeah, in a way, I think it's getting there. I think in my head somehow. So, because this little e with a tail, big e with a tail, this represents the frequency. And one of the questions that I had was like, okay, so why is these here specifically, right? It's by design here. It's the only place in the equation where this is, and so it's got to do something with. And it definitely it's got to do, because that's the frequencies that we're then looking for, right? And say, does this function have like frequency 1, for example? And so by virtue of the fact that this is here, this means that this affects the angle. Because if you plot, so this is like the basically, what way you're plotting things, this is a factor, like the factor that multiplies the I in the exponent tells you how far you're rotating. So frequency 0 would just be e to the power 0, frequency 1 is e to the power of 2 pi, so it's kind of, it stays in the real lines, right? Here in this case. But then as you're picking up different frequencies, that's gonna start moving in the complex plane, right? For example, yeah, but they're all like, what's interesting is they because of the fact that there's a minus 2 pi, right? It means if we just think about like integer, not in, is it integer the right thing? It's, or just even just let's think about the natural numbers, right? Like just think about like, okay, these are real numbers, but like just make it simple. Let's just think about frequencies like 1, like 2, 3, 4, 5, right? These are always going to be multiples of 2 pi. That's what you're doing, right? So I don't know why does this make a difference, because like 2 pi is the full circle, is it? Like e to the power of 2 pi, no, 2 pi I is 1, right? So that is the that is like the full circle. So in a way, what this frequency is saying is like how much is this somehow contributing, because you're multiplying these with the function, right? And so I think the way this works is that if a frequency is not there, right? Maybe let's try to decompose that. If a frequency is not there, then somewhat we're looking for cancellation effects. So we're looking for things that go in the complex plane, because then you can kind of do a bit of the interference thing. I'm not so sure if this is the right way to talk about it, but how could we make about an example? Just have a simple example. Fourier transform, simple example, because Fourier transform. Simple example, not explanation. The Fourier transform, because here we got some functions. Yeah, okay, but you see, there's a single frequency. So actually, like if you'd have like a cosine wave, you should have a single frequency. So that's really what we want to have, right? That's why my example with the sine function was what I thought was good. But maybe I'm just using the wrong frequency or the wrong formula, because it seems like here we're talking about W. And so here, for example, right, it's a bit of a different formula. W is directly here as a, I don't know what this minus J, okay, it's just W. Okay, so there's no 2 pi, the 2 pi factor in there. So that's the ordinary frequency maybe, and then maybe if we take a look at the angular frequency, maybe this is what we should look at. Look at this. Because of the angular frequency is defined like that, then probably it simplifies that. What? It simplifies that that thing to like W. So let's just work out from the, it's just W instead of 2 pi. So like the 2 pi goes away. So literally it's just W. It's a factor of I. Well, and then there's X as well in there, right? To make it more complicated. To make it even more complicated. No, there's no X. Yeah, there is. There's T in this case. Yeah. Yeah. So the Fourier transform. Let's open up again Paint. So if you'd go ahead and do and do like a cosine wave. So let's say f of x is cosine, the cos of x, right? So and now we have the Fourier transform being the cosine of x times e to the power of minus I, then the frequency, and then x dx, right? So this is kind of the parameter, I'd say, right? And so now, like, we know that in theory, so if you have the cosine wave like that, in theory, what we expect the Fourier transform to be is a function that's like these, right? Because it's a single frequency. It's a single frequency, and this is basically, I think it should be 1, isn't it? So Fourier transform of cosine of x. Maybe that's what we should. So here, but why is it that complicated thing here? Because I think these things here is, again, it's a funky mathematical way to define chunks, I think, or to define something that is just not a continuous function, I think. And I don't know, I really don't know what this is. Never been with that before, played with that before. Okay, so they go, okay, here they go actually with 2 pi, right? And so what they do is they solve the integral like these. Okay, so why? So these would give you a, God, what is this thing? What is these? I saw that I came across this in 1 or 2 videos ago, I think. Pairs. How do I even search for, like, settings? I want to copy that. So exactly the delta function. The unit impulse symbol is a generalized function or distribution over the real numbers whose value is 0 everywhere except at 0. Okay, so it's a function that basically gives you 0 for everything, but then gives you something different for 1. Every continuous function to its value at 0. Okay, so it's just like that. That's the that's what it is. Okay, that's a smart thing to. So that's okay. So it's an interesting. How do you get there? That's another. Like I would have never been able to do that. So how? So this is derived like these, and then at some point they're like, fuck it, we'll just use that. So, God. So what this is saying is like, you do this subtraction, this addition, and then you yeah. Wow. which the only thing that in various situation. Let's try to think about this on our own, right? But I think so. You have cosine of x, and then you have these. Yeah, well, I think it's the same. If you have the 2 pi here and stuff, then you use the 2 pi function with the classical frequency. But in this case, if we just reformulate it like that with angular frequency, that should actually work well. Because then we're getting rid of the 2 pi and 2 pi everywhere. But again, why is that relevant, right? And I think here what they do is they expand that into they go with ease, right? Because it's easier to integrate. That's okay. They use the fact. Yeah, okay. So they use that thing. I also saw that. Yeah. I also saw that here in the Wikipedia, I think. Oh God, I'm lost here. This one. Yeah. They use the fact that you can express things like these. And so they use the fact that you can express the cosine of something as in like the sum of, these factors with the exponentials being negative and positive, and so that makes the integral easier. So in this case, because okay, 1/2 of this stuff, right? So I'd say basically what we're saying here is that this cosine component kind of decomposes into like that little thing there. So half e to the power of IWX plus half of e to the minus by 5 the x, and so that is basically equal to cosine of x times e to the power of 5 minus IWX, right? And so then you kind of do the distribution, right? And then you end up with like half of e to the negative, so I times I is -1, but there's a minus, so it's 1. So this is like Wx, right? Because we're multiplying, so we're multiplying, so we're adding. What am I doing? So what we're doing is we're multiplying, so we're adding the exponents, right? Which basically are 0. Which basically means that its e to the power of 0 is 1, right? So I'll just e to the power of 0. And in this case is basically, and it's like minus 2i wx, right? And so we're like left with integrating these thing. I mean, this is a constant, and then we have these here. And so what do they do? I mean, here there's this frequency stuff, so here the terms don't really go away. This is where I'm stuck. Okay, that's the work of this person. Okay, and that's what's, yeah. So what he's doing wrong is he's having this function here, I think. So extend the notion to include what are called distributions or impulses or Dirac deltas, or as we engineers I want to do it much to the disgust of mathematicians, delta functions. And you will see that cosine does not have a Fourier transform in the usual sense. Turning to a specific question, once you understand that impulses are defined only in terms of how they behave as integrands in an integral, that is, let's see, to deduce the Fourier transform of by musing on the fact that, what the fuck, I have no idea how you get there. Then just use the table of Fourier transform pairs. What the fuck? Oh god, what? Useful integrals, blah 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 blah. Yeah. Fourier transform. I have no idea what that is. But I have no idea what that is. So why doesn't the cosine function have? This is what I don't get. This thing with the Dirac delta functions is it's a little dirty trick, man. It's definitely a little dirty trick. I like it. Here was a good example, but here the problem is that they use this kind of funky function, and I just wanted to understand why Fourier transform of cosine function. Right. Converge, yeah. Oh, there's the video. Let's take a look at it. Nice commercial about cats. Come on. Not gonna pay for a pro account for
calculated the Fourier transform of e power j omega naught t, and we found the Fourier transform. Find the Fourier transform z, and we have, so let's see how we can calculate the Fourier transform x omega. We can write cos omega naught t e power j omega naught t plus e power minus j omega naught t. Now I will take Fourier transform on both the sides. So we have Fourier transform 1 over 2.
Why not?
To Fourier transform up naught equal delta x omega naught omega minus transform of cos omega naught phi multiplied omega naught. Calculation of. So this is all for this lecture. See you in the next one.
Why not? So here they say it's not an absolute integral signal. Cosine absolute integral. So for instance, here, the integral. Okay, so maybe this is okay, maybe this is a. This has got something to do with sort of the requirements for these to work out well, and that's why it doesn't have a well-defined Fourier transform. An integral function. Because it's non-negative, because it's negative, maybe an integral non-negative function. Okay, so in mathematics, the integral of a non-negative function of a single variable can be regarded in the simplest case as the area between. Okay, no, sorry, forget about that. History definition. So why doesn't it work well? I don't understand that. But maybe let's try to step aside. This is what I'm trying to understand why the E kind of thing makes sense, right? In this case, oscillates at 3 Hertz. So in 1 second, it does like 1, 2, yeah, kind of. So it's 3 times more or less, yeah. Right. Now, what is it that makes it? The thing is, I'm not even sure myself what I'm trying to understand. So I'm trying to understand why the complex exponential it's what makes sense in this case. Why is it that's, you know, that why does this function make sense like that this definition? Because you've got your function and then you're multiplying it by this factor, where how could we plot this? How could we plot this without these without the frequency parameter, just to understand what is it that's happening here? So that's why I was trying to take a simple example of like the cosine function, because I could just maybe say, look, cosine times these, and then I understand what's going on, right? But I don't know why it seems like the cosinus is not the good one, and I'm trying to understand get a simple example. But I could still try to take this function and go to Desmos. see if I can this must plot that. X E so E to the power of, no, how's power? What is it that am I doing? Cosine minus x, okay, x squared. Interesting. But okay, let's zoom into these. So this is what we have, and then if I like what would be the function that results when I multiply? I'm trying to visualize that because I want to see now I'm multiplying these by this function. I'm asking for the integral, right? So I'm multiplying these by this complex exponential, which is a function then of x as well, right? So for example, let's say the value at 0 is 1, right? So when x is 0, so now we have this funky function, but I say when f of x, so f of 0 is 1, right? So in this case x equals 0. If I now have this other function that is basically f of x times e to the minus minus pi x squared, right? So when x is 0, what I'm getting at here is because here we're assuming now that the we're doing that, so I'm assuming that the frequency, we know it's 3 hertz, and so I'm assuming the frequency, this like E whatever it's in this case, that this kind of thingy here is 1, right? So I'm not including it here, and so that's pi, by the way. No, what am I doing? You see, that's how you make mistakes. It's e to the power of minus 2 pi I x, and then this thing here, right? Is that correct? Yes. What is this visually doing to the result? So when this means that when f of 0 is 1, right? So this g of x thingy here is just going to be e to the minus, it's just going to be these, right? What is that? What does this mean? What does this mean? This means the integral is then the same, right? So this is really this kind of just this circular thing, which which basically means, because I'm looking at, so this is at the point where this is 0, and so it equals 1. What am I doing? And I want to understand, so that's the function that I end up with, right? You know, f at f equals 1, no, at f 0 to 5, for example, is equals 0, and so basically g of x is in this case 0, right? Because remember, what we're integrating is like so. I'm trying to visualize that, and it's so hard. Like it's so like I'm getting lost somewhere along the way. I'm getting lost hard somewhere along the way here. Because what it seems like, t and t. Okay, so because here the 3 is just as 3t, and then it's a function of t. That's what's also confusing me at the moment here. But based on this example, what I can... because actually I have the plot here. To be honest, that's actually not bad. I have the plot here actually. So I shouldn't even be doing it. I don't have to do it by hand. So I have the plot here of what this means. So, but it's funny. So it's funny that for some reason, when you multiply this function by this complex exponential, you're getting that thing that is only positive, right? For example. Whereas this is the real part. This is the complex part. So the real part is only positive. That's what it's actually saying. Okay, because what they do is you have to think that a e is, you can do as a sine plus cosine, right? So you multiply a function by sine plus cos plus I cosine, and so this gives you so if this is my function and I multiply it by a cosine of something, because I should be able to plot those things separately. This is my function. And then what I'm doing is I'm multiplying it by these, right? And then this is a plot of the real part and the complex part. Minus 2 pi 3t. Okay, so let's try to do this the way it's written here. Cosine of 2 pi 3x yeah, okay, but that's kind of okay, right? That's what we have. 2 pi 3 times 2 is 6. 6 pi x, 6 pi x. Okay, so that's, I mean, that's correct. And then what if we multiply this by that? This is so one way to think about this is this guy here is cosine of not of x, of course, cosine of minus cosine of 6 pi x plus I sine of 6 by x. So that, and then we're going to plot these two things separately. But is that correct? Because the one is the Euler's formula. It's plus, so when it's minus, it's both minus. Okay, so it's both minus, whatever. So times minus cosine of 6 times pi times x. Interesting. Yeah. And the sinus actually gets that. So this is okay, so this is, I think, where I have to start next time. This is where I have to get. So okay, so what this is doing is you've got a function. Oh my god, but that's just because it's a 3, right? So we're doing 2 times 3, right? And here it's like 2 times 3. But apparently these 3 changes things. If I just say, well, what about frequency 7? Frequency 7, yeah, well, we have the same story. Frequency 1, that does not seem to depend on the frequency. You always get the real part that adds up, you know, and that it integrates to something that's not 0. Why does 5 specifically? Oh well, of course. That doesn't change. That's the function that I have. Look at these. Okay, so I know I get it. So 1, 2, 3, 4, 5, 6, 7. Interesting. So only when the frequency is matching, you're getting, that is why. So only when the frequency is matching, you're actually getting a result that integrates positively. That is really cool. And this is essentially, I think, because if you have cosine of x, say cosine of 3x, this cosine of 3x, right? So you've got something positive. If I change that, that is the reason. That is the property that we're exploiting, in a sense. Only when the frequencies match, nice. Only when the frequencies match, you get that result. Why is that? Why is that? If we plot things separately, cosine, and then say cosine of 3x. well, it matches, so this means that the negatives cancel out and become positive. As I change that, the things don't match, and so you're not gonna get a positive result only. Like, you're gonna get, something times, there's gonna be negative, and then 2. So as you match, okay, it makes sense. Now it makes sense why do we want to use an integral, and it makes sense why do we want to use this e thing, because what this e does is it decomposes into the cosine and the sine. I don't know why is it necessary to generalize it to so much that you kind of go to complex numbers. I don't know why you need to generalize it so much, but I guess in a way that makes sense. When the frequency is matching, the okay, but that was a simple case of a cosine, like of something that looks like these, right? When the frequency is matching. But what if you have a combination of? That's what's interesting, right? I guess if you have a combination of things like, yeah, that's then more complicated, but it's probably the same in a way. In a way, when you match one of the frequencies, these numbers don't cancel out so much, and so you get an integral that is positive, that is non-zero. That'll be next. Let's try to find an example that actually has a more complex thing. So it actually has a function that it's a combination of multiple frequencies. I mean, what if cannot you just say cosine of like 5x, right? So you have these. If you plot them together, it's this big thing here. And so now when you say 3, no. Well, now we're gonna multiply these by cosine 3x. You see, and it's almost, if you do 5, it's also almost, but if you do 4, yeah, then I don't know how that works. How would that work? Because then is when it gets nasty with the Dirac delta functions. Okay, so that's still something to explore next time. Thank you. It's been a bit longer than expected, but not bad. Thank you. See you next time. My outros are awful, man. I shouldn't just say who am I talking to? Thank you. Good session.